we are going to do section 4.2, which consists of area. Now, area, we're going to use a lot of sigma notation, and sigma notation is the giant E, and what that E means is the sum of n terms, 1 through n. You can see the A of I is the ith term in our definition, I is the index of summation. Our terms go from 1 to n, so from the bottom number to the top number, and we're pretty much just plugging each one of those into whatever our A is. A is generally going to be some sort of function, A of I. So some examples of sigma notation, we just have I equals 1 through 6 of I. So what we would do is plug in the 1 for the I every time, and it goes up 3, 4, 5, and 6. We could add that together, but just to illustrate what the point is. So for this one, it's I plus 1, but our index goes from 0 to 5. So 0 would still be 1, and then we're going to start at 1. That's going to be 2, and then 3, 4, 5, and it's actually going to look exactly the same as the last one, even though the functions are different and the indexes are different. Okay, j squared. So we start with 3 squared, which is 9, plus 4 squared, which is 16. We'll just put in the actual values. Plus 16, 5 squared, 25, 6 squared, 36, and 49, which is 7 squared. Next one we have 1 over n times k squared plus 1. So this one we're going to have a physical number like a, b, and c had, that we can't really put anything into the n's. So that kind of stays out front. And then the k squared plus 1, we're going to put in the 1 all the way up through the nth term in for k. So that's 1 squared plus 1 plus 1 over n times 2 squared plus 1. And that pattern is going to continue until we get to 1 over n times n squared plus 1. Because n is the last term, that would be where we stop. In our E, we have f of xi times delta x. 1 to n is our index. So we're going to have f of x1 delta x plus f of x2 delta x plus all the way up to f of xn delta x. That's not going to make any sense to you right now, but it definitely will be looking familiar towards the end of our section. And here we have the summation formulas that we will be using throughout the section and the next section. So we need to familiarize ourselves with these. I will give you these for any quiz or test. You don't need to memorize them, but these are probably the ones we want to use, are the ones that are multiplied out. And that one. Okay, so just make sure we know where those are. Evaluating a sum, we have I plus 1 over n squared when n is 10, 100,000, and 10,000. So that, like we saw in one of those last examples that we illustrated, those n's, you can't put anything in for the n's. The i's are the only thing that gets evaluated. So we can actually just pull that 1 over n squared out, and then our index will only deal with the i's. Okay, so let's go ahead and we can also separate the sum of I and the sum of 1. Because as we could see from our summation formulas, whatever that constant is, your answer is just going to be n. So this summation here is just going to turn into n, and this summation is going to just turn into n squared plus n over 2. So now we can just substitute those in, and that's the good part about simplifying and pulling those out, is that we can just go ahead and substitute. So n squared plus n over 2 plus n. We would want to get a common denominator, so this would be 2n over 2. 1 over n squared times n squared plus 3n all over 2, which is n plus 3 over 2n. and that would be our evaluating. We're going to put in, once we simplify it all the way down, we're going to put in 10, 100,000, and 10,000. So we put in 10, it's 10 plus 3 over 20. We have this on the side over here. N is 10, 13 over 20. N is 100, 103 over 200. N is 1,000, 1,003 over 2,000. And N is 10,000. That's 10,003 over 20,000. We could probably just leave it as those fractions. Okay, we are asked to use 5 rectangles in a figure to find 2 approximations of the area of the region lying between the graph of negative x squared plus 5 and the x-axis between 0 and 2. So if we're asked to find 5 rectangles, then we're going to have 5 different intervals. If we're starting at 0 and ending at 2, we have to consider, okay, so we have to break that into fifths. 0 to 2 divided by 5. So our first interval is going to be from 0 to 2 fifths. Second one's going to be from 2 fifths to 4 fifths. Second one's going to be 4 fifths to 6 fifths. 6 fifths to 8 fifths. And 8 fifths to 10 fifths, which is 2. Okay, so they're asking us to find 2 different approximations. So one of our approximations is going to be using the right endpoints. And those right endpoints are going to be a width I, and those are always going to be our index. We're going to have width I, and our right endpoints are going to be 2 fifths I, because that's the width of each one of our rectangles. And our I is 1, 2, 3, 4, and 5. So our first summation is going to be from 1 to 5, f of 2I over 5 times 2 fifths. And we have these 2 different, this is the height of our rectangle, and this is our width. We know that each rectangle is going to have the width of 2 fifths, and f of 2I over 5 is going to be using the function to find out how tall the rectangle is. And we're going to try to simplify this as great as we can. So f of 2I over 5, we're going to use our function negative x squared plus 5. So that we get negative 2I over 5 squared plus 5. That's our f of 2I over 5. And we're timesing by 2 fifths. And going from 1 to 5, I'm going to simplify it for you to save a little bit of time. We get 162 over 25, which is 6.48. Okay, so those were our right endpoints. And we're going to do the same thing with left endpoints because they wanted us to get 2 different approximations. Okay, this time our endpoints are not going to be 2 fifths I, they're going to be 2 fifths I minus 1 because we need to get to the left side, so we subtract 1 from it. And again, our I is going to be 1 through 5. So we're actually going to do the exact same thing as we did with the right, only our f of is going to be f of 2 fifths I minus 1 instead of 2 fifths I, which will make it a little bit more challenging. I distributed the 2 into the I minus 1, which is how we got 2I minus 2 times 2 fifths. So now we're going to put that into our function. And skipping the hard stuff, you can also just type that into our calculators to figure out what the summations are at that point. We get 202 over 25, which is about 8.08. So because we have the right endpoint approximation and the left endpoint approximation, we know that our area is going to be somewhere between those two. Okay, now we're going to be able to approximate it a little bit better. So we have upper and lower sums. With any plane region, any non-negative continuous function, we have an interval a to b that's divided into n subintervals where the width is delta x, so b minus a over n, which is we had 2 over n because a was 0 and b was 2, which gives us 2 over n. Little f of little mi is the minimum value, and f of capital Mi is the maximum value. I'm going to draw some pictures down below which are going to explain the inscribed and circumscribed rectangles. Okay. So we're going to have the same function every time. Or very similar. So inscribed is where all of our rectangles lie underneath, never cross over the function. Okay, so it looks something like that. We're going to go over to the right side. This is going to be our circumscribed area, and every time our rectangle is going to go above the function. Okay, so get the general idea. The inscribed area is obviously less than the actual area because there are a couple of gaps underneath the function, and the circumscribed area is greater than the area, being as we have rectangles that go over the top. And our goal is to just find some way, find our actual area under the curve. Okay, that's our actual area. So that's pretty much what we are explaining up above. I just thought the pictures would visualize a little bit better. Our area of the inscribed rectangles is less than our actual area. It's less than our area of circumscribed. Okay, so we have two different sums. We have the lower sum and the upper sums. We need to stop here and finish the section 4.2 in the second video.